In the winning sweep by Binary Mechanics Lab of all major physics research events, the hard-hitting exposure of the weak force debacle won first prize in the Best Physical Force Mathematical Definitions competition. This is the dramatic, emotion-packed story of the downfall of physical force definition based on supposed particle interactions, in which many physicists and Nobel Prizes were lost on a flooded road to nowhere. Most physicists currently list several variations of weak forces as primary fundamental forces of nature, based on analysis of particle interactions. In binary mechanics, time development of any system state is exactly determined by 4-bit operations: unconditional, scalar, vector, and strong, based on a pair of relativistic Dirac-Spinner equations of opposite-handedness. The table above maps supposed primary forces in legacy physics to these underlying mechanisms of time evolution. The traditional weak force category maps to the unconditional bit operation, right here. The unconditional bit operation produces these particle interactions. The W and Z bosons identified as related to right-handed matter d quarks. However, the unconditional bit operator is based on the momentum component in the Dirac equation and is further differentiated from the binary mechanical primary forces by their mathematical definitions. Scalar, vector, and strong are the primary forces. The unconditional bit operation, which is a bit shift, the defining parameters for a force, which are listed here, are not applicable. As a result, particle interactions that had suggested new weak forces could be accounted for by the unconditional bit operation, and therefore weak interactions do not represent a primary force of nature. It's about that simple. This paper examines some weak interactions to illustrate that their basis is the unconditional bit operation. Let's look at two-spot cubes. 4 spots are partially visible in each spot cube, left and right. 1, 2, 3, 4. The electron in yellow and the 3 d quarks. 1, 2, 3. 3 of these 4 spots, the electron, the blue right-handed d quark, and the green right-handed d quark, represent matter, while DRL is an antiquark or antimatter, shown in pink above. Each color-coded spot is a 2 by 2 by 2 cube of bit loci. A spot cube contains 8 spots, 4 of which are partially visible in this view. Electron spots in yellow, and the left-handed, that's what the L here means, the left-handed electron, and right and left d-quark d spots, red, green, and blue. Fermion mite or M-type bits, the circles, and boson photonic and gluonic light or L bits, the arrows in the stars, are shown also. Stars are lights moving toward the viewer, here and here, for example. Purple arrows indicate the direction of the 3 interdimensional strong bit operations within a spot. These are the purple arrows, there and there. Same over here for the other spot cube on the right. Possible unconditional bit operation sequence is shown by the red arrow. From this electron spot, all the way shifting to the right in the unconditional bit operation to the next electron spot in the next spot cube. Beta decay producing a free electron. Using Feynman diagram format, the spatial dimension x versus time the binary mechanic basis, upper, for the beta decay diagram, lower. Here's the beta decay diagram, and here is the binary mechanical basis. Fermion M loci, the circles may be in the 0 state white or the 1 state gray. Here at the earlier time, we have a neutron and an empty spot cube, showing the mite bits here are in the 1 state, indicated by their gray coloration. First, the location of the electron antineutrinos is the electron spot 0 state M loci in the spot cube that initially contained a neutron, the bottom left, but then is converted to a proton, the top left. Here are our neutrinos, which are 0 states because the 1 state bits have moved by unconditional bit operation to another spot cube and its electron spot. So we start with a neutron and an empty spot cube neighboring it, and with the passage of time indicated in the Feynman type diagram, we have a proton without the electron and free electron in a neighboring spot. For simplicity, the electron final state, the top right here, is depicted as an electron in a spot cube without d quarks. In the electron bit cycle, 1 and 0 state bits circulate in opposite directions. That is, the handedness of the 0 state M bit must be opposite to that of the electron 1 state M bit. Therefore, the 0 state bits that remain after its 1 state bits move to another spot cube unambiguously represent electron antineutrinos. The unconditional bit operation alone may, in successive steps, shift the 1 state electron spot unit bits, bottom left here, through the blue d quark to the adjacent spot cube on the top right. Here they're moving through the d quark and to the adjacent spot cube. 3. If 2 other surface views of the spot cube are included in the analysis, the intermediate spot could be a red, green, or blue d quark. In all cases, matter is preserved. Fourth and lastly, the binary mechanic basis reveals the true identity of the W gauge bosons. Namely, they correspond to events in d quarks. Now, this W boson could be plus or minus, and that would have to do with the slope of this curve, and we'll let the experts in Feynman diagrams of this type work that out for themselves. Now, what about neutron-proton exchange beta decay? This is very similar to what we just looked at, except rather than having an empty spot cube on the right, we've got a proton, and this spot cube contains a neutron. With the passage of time, they switch positions. With the electron movement to the right spot cube, it becomes a neutron, leaving the left spot cube as a proton. Neutron-proton exchange in atomic nuclei, supposedly mediated by a Z-gauge boson, exhibits similar processes and conclusions described above for beta decay releasing beta particles. That would be electrons. In this case, the Z-gauge boson is also shown to represent events in a d quark spot. Weak force, the road to nowhere. The portrayal of weak interactions as a primary weak force set has the appearance of having value, but instead qualifies as the weak force boondoggle. Binary mechanics may now have depreciated the weak force to events incident to the unconditional bit operation as a fairly well-settled issue. In the 2011 paper, on binary mechanics postulates, several examples of weak force interactions analyzed were entirely accounted for by the unconditional bit operation. Remember in our table at the beginning, the unconditional bit operation is not one of the primary force, rather it's related to the momentum operator in quantum mechanics time development treatments. Without the discipline required by binary mechanic postulates, investigators observing weak force interactions would have not known this, nor would grand unification analysts have attempted to unify the weak not force with electromagnetism into an imagined electroweak fundamental force. This is a complete snafu. In retrospect, it may now be clear that the confusion regarding a supposed weak force arose perhaps entirely from lack of a rigorous definition of a fundamental force in physics, such as defined in binary mechanics. This precise mathematical criterion replaces the present chaos that whenever some purported particle interaction is observed, the physics community may rush to postulate a new fundamental force without any specific discipline on the required criteria for a fundamental force. This weak force snafu illustrates the utility of a formal definition of fundamental force in physics. Without it, almost any observations of apparently new phenomena that do not readily fit into current theories may result in proclaimed discovery of a new force. And oh, we need to name a new boson to mediate these interactions. And on into seemingly endless confusion. And boy, do we have that if you consider gravity, gravitons, WIMP particles, all of this nonsense. Theorists can determine if they have the goods to declare discovery of a new force by filling in a new row of the mathematical force definitions shown above with their specific new force defining components. Here we have the unconditional bit operation on the top related to momentum. Here we have the three fundamental forces. You'd have to add a new row and fill in the blanks for the three items required to define a fundamental force. And that's all, folks. Thanks for watching the show. Hope you enjoyed it. Bye bye.